Hello everyone and welcome back. My name is Mr. Covalt, and in this video we're going to go over how to calculate the Kc and the Kp for the dissociation of iodine into gaseous atoms. So let's get into this. Okay, so here's the problem. When 1.00 moles of I2 gas is introduced into a 1.00 liter container at 1200 degrees Celsius, it is 5% dissociated into Ig gas or gas iodine atoms in the gaseous phase. So then they're asking us, well, calculate the Kc and the Kp values for this situation. So the first thing we want to do is write out the balanced equation of what's going on here. So we're dissociating I2 gas into individual atoms of iodine gas. So if we write that out like so we have I2 gas, and that's going to dissociate into 2I gas. And so this is at equilibrium. So if we have our double arrow there, we can write out the K expression, Kc. So in this case, we have Kc is going to be equal to the concentration of products over reactants, right? So that's the general equation or simplified version of the equation for the equilibrium constant. We're going to calculate Kc because look what they gave us. They gave us 1 liter volume, and they gave us 1 mole, and concentration is moles per liter. And so we can write out the expression for Kc. And so here we have the product I, single atoms of gaseous iodine, and it has a 2 coefficient. So we're going to write that as the concentration of I raised to the power of 2. And then we've got this gaseous iodine there in the diatomic form. So we're going to put that on the bottom since it's a reactant. So we have I2 concentration like so. So here we have our Kc expression. So all we need to do is find the equilibrium concentration of the I and of the I2. So in order to do that, we'll have to write out a ice table. You don't have to write out the ice table, but in this case, I'm going to write out an ice table to kind of show you how we get our values. So here, I'm going to have an ice table here. So I'll write it down here underneath here. So we have ICE. And we're told, since we have 1 mole per 1 liter, then that's a molarity of 1. So we'll have 1.00 molar here for the I2. We start off with 0 initially. And, well, how do we figure out the rest? Well, we are told that there is 5% dissociation. So that's the change in our table. So what is 5% of 1.00? Well, it's 0.05. That's the change. And so since we have 0 amount over here, we know that the equilibrium is going to shift this way. We're going to make product. So the change here is a negative 0.05. And notice here there's a 2 there, so the stoichiometric ratio is 1 to 2. So whatever we lose here, we're going to gain double that amount here. So we gain 0.10 amount here. And so we end up at equilibrium. We're going to have 0.95. So we have 0.95 here, and we have 0.10 here. So we at equilibrium, we have 0.95 molarity of the I2, and we have 0.10 molarity of the I. Now we have our concentrations that we can plug into our expression. So let's go ahead and do that. So we have I squared. So we're going to put 0.10 squared. And then here we have I2, that's going to be 0.95. So we're going to put that down here, 0.95. And then when we calculate that, we get 0.105. So this is going to be 0.105. And if we round that to 2 sig figs, because we have 2 sig figs here, 2 here, so then rounded to 2 sig figs, that would be 0.11 for our Kc. Okay, so now what about Kp? Well, Kp, as we said, is going to be Kp is equal to Kc times RT raised to the power of delta N. And the delta N here is the difference in the moles, the gaseous moles of products and reactants. So we'll have the gaseous total moles of gaseous products minus the total moles of gaseous reactants. And so here we look at the gaseous moles. Here we have 2 moles of single atom ions in the gaseous phase. So if I calculate delta N here for the products would be 2. So 2 moles of the products minus the moles of the reactants. We have 1 mole of the reactant I2. So we're going to subtract 1 from there, and delta N is 1. So then when we write our equation, we can plug everything into the equation. Okay, so let's go ahead and do that. So we have Kp. So Kp is going to be equal to Kc. We calculate Kc here. We're going to go ahead and use this value here with an extra digit so we avoid rounding errors. So we're going to have 0.105 times, and then R, of course, is 0.08206. Okay, and that's going to be, oh, and by the way, this is, I should rewrite this so we have this available. So this is, again, this is in terms of molarity, right? So we're going to have moles over liter. And so then we're going to multiply by R. So we have 0.08206, and that's going to be liter atmospheres over Kelvin mole. And then we're going to multiply that by the temperature. And the temperature, they said, was 1,200 degrees Celsius. That's in Celsius, so we have to convert that to Kelvin before we do anything else. So we have 1,200 degrees Celsius. We add 273.15 to that, and that's going to give us 1473.15 Kelvin. So we're going to plug that in here. Okay, so that's going to be 1473.15 Kelvin. And since this is a 1, the delta N is a 1, just to kind of make it clear, so I'm going to put square brackets around this, and that's a 1 there. Again, I didn't need to do that, but I'm just showing you how we're plugging everything into the equation here. And so now we have moles canceling out, liters cancels out, Kelvin cancels out, and we have atmospheres left. And so now all we have to do is calculate this with our calculator, and we get 1.272. So Kp is equal to 1.272 atmospheres. Okay, and so again, sig figs are important. So remember, we only have 2 sig figs here. We kept an extra digit to avoid rounding error. So we have 2 sig figs here, right? So it ends there. And so this is 4 sig figs. This is 4 sig figs, or 6, 4. Or if we look here, it's 2 sig figs because there's no decimal point there, so these zeros are not significant, so we have 2 there. So the final answer here should be 2 sig figs. So if we round, it should be 1.3 atmospheres, and so that is the Kp value for this equilibrium reaction here. So I hope this was helpful. If this was helpful, then please, by all means, like the video, share the video, hit that like button down here somewhere. Subscribe to my channel. Don't forget to do that, and hit the notification bell above, so that way when I put up more videos, you will get notified by them, and you can watch till your heart's desire. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.